አይ ሰላም ናችሁ ወይ? አይ ቲንክ ክላስ ያሉት ጆይን ያደረጉ አይመስለኝም። ይሰማችኋል እናንተ? ክላስ ጆይን አድርጋችኋል? የሙሉ ቀን በሙሉ ቀን በሚለው ነው ጆይን ያደርጋችሁት? ብዙ ስለማይሰማኝ እስኪ አንድ ሰው ያወራ። ምንም ድምፅ አይሰማኝም ሚውት ስላደረጋችሁ ሁላችሁ።
ፕሮጀክተሩ አይሰማም።
ይሰማችኋል?
ፕሮጀክተሩ
ይታያችሁ?
አይ ገና ነው እንትን ሴት እያደረግን ነው። ዲስፕሌይ እያደረገ አይደለም። ዲስፕሌይ እያደረገ አይደለም።
ከኔ ጋር ነው ችግሩ? እናንተ ጋር ገና አልተጀመረም?
እኛ ጋር ነው ችግሩ።
ኦኬ ኦኬ ፕሮጀክተሩን እስከምታስተካክሉ ለምን አንዳንድ ነገር አላወራችሁ? ባለፈው እንደነገርኳችሁ ላብ አለን ብያችኋለሁ። አንድ 4 የላብ ስኬጁል እናደርጋለን ብዬ ልኬላቸዋለሁ ለምን አቡበከር እና ከዛ አሲስት እናደርግ ሰው እናዘጋጃለን ብለውኛል። ግን መሽመሽ ነው ላቡን ልሰሩ የምትችልባቸው 1-3 ሰዓት ፈልጋለሁ ለእያንዳንዱ ላብ። ስለዚህ 4 ከሆነ በአራቱ 4 ሴሽን ያስፈልጋል። እና እንዴት ነው እንደዚህ አይነት ነገር ሲኖር ኖርማል እንዴት ነው የምታደርገው? ኖርማል ክላሱን ነው የምትጠቀሙት? የክላሱን ፋይል
ምን አልከኝ? አዎ አይ እንትን ያደርጉ ስላሉ እኮ ነው ኤርፎን ያደርጉ ስላሉ። እሺ አይ ቆይ እስኪ እንትን እያደረገ ነው ለቴክኒሻኑ መጥቶ እያስተካከለ ስለሆነ እያስተካከሉ ስለሆነ ብዙም አይሰማም፣ ግን እያስተካከሉ ነው አሁን። ኦልሬዲ 1-2 ደቂቃ እየጨረሱ ነው።
ኦኬ አይ በቃ የማይሰማ ከሆነ እጠብቃለሁ። ችግር የለም።
እሺ
የሚሰማ መስሎኝ።
እሺ
እየተናገረ
ኦኬ ብዙ ማይኮች ስለተከፈቱ ክላስ ውስጥ በጣም ኢኮ አለ። ስለዚህ ሚውት አድርጉ። ብዙዎቻችሁ አይ ቲንክ ኦን ናቸው። አይ ቲንክ አንድ ሰው ብቻ ይበቃል። የኤልያስ ይታየኛል፣ ሚውት አልተደረገም። አይ ቲንክ ሌሎቻችሁ ሚውት አድርጉና መደማመጥ እንችላለን። ዮናስ ሚውት ላርግ ነኝ ከዚህ ኦኬ አሁን ይሻላል። ይሰማችኋል አሁን? ይሰማል?
ይሰማናል ዶክተር ቀጥል።
ኦኬ እሺ ይታያል ስላይዱ ማለት ነው። እንግዲህ እንደዛ አድርጌ ነው የምገምተው። ኦኬ እያልኩ የነበረው ባለፈው ላብ እንሰራለን ብያችሁ ነበር እና አንድ 4 የላብ ሴሽን አዘጋጅቻለሁ። ለና አቡበከርም አውርቻቸዋለሁ እንደሚያዘጋጁ ነግረውኛል። ሰው ግን በስኬጁሉ በዚሁ በኖርማል ታይም ነው የሚሆነው ወይስ ለብቻ የላብ ስኬጁል አላችሁ የሚለውን ለመጠየቅ ነው። አንደኛ ዲስከስ እናደርጋለን እሱን። ስለዚህ 4 ሴሽን ያስፈልገናል። እያንዳንዱ ሴሽን 3 ሰዓት አካባቢ የሚፈጅ ስለዚህ አይ ቲንክ ሴሚስተሩ ምን ያህል እንደቀረው ነገሩኝና አይ ቲንክ የሰማሁት 1 ወር ከምናምን ነው። ሴሚስተሩ ለማለቅ የቀረው ምን ያህል እንደሆነ ካወቅን ይሄኛውም መጠቀም እንችላለን። ኖርማል ክላሱን እንደ ላብ ሴሽን ወይ ደግሞ ለብቻ ላብ ሴሽን ሊያስፈልገን ይችላል። እና እስቲ አንዳንድ ነገር ንገሩኝ እንዴት እንደምትሰሩ ስለማለቅ እዛ። ኤልያስ እያወራህ ነው? አይሰማኝም። ያንተ ሰማው ማይክ ኦን ነው ግን አይሰማኝም። የክብሩ የሚለው ጋር መነጽር ያረከው ልጅ ይሰማኛል። ያንተ ሜቢ አንተ አውራ
እና ኤልያስ
አሁን ይሰማል። ሁለት ማይኩን ኦን አድርጓል እና ኤኮ አለው እኔ ጋ። እስቲ አሁን አውራ። አሁን ይሻላል? ኦኬ ያ አይ ዶንት ኖ የመደማመጥ ችግር አለ ሰምሃው። ስለዚህ ሜቢ በዚህ ጊዜ ከምናቃጥል አስቡበትና ኮሚኒኬት እናደርጋለን በቴሌግራም ወይ ደግሞ በኢሜል። እናንተ ዲስከስ አውሩና ምን አይነት ሀሳብ እንዳላችሁ ለኤልያስ ትነግሩልኛላችሁ ወይ በኤልያስ በኩል ንገሩኝ። አሁን ግን አልሰማችሁም። ሰምሃው አንድ ሰው መናገር ሲፈልግ ኤኮ አለው። አይ ዶንት ኖ ምን እየሆነ እንደሆነ። ስለዚህ ጊዜ ከምናቃጥል ዝም ብዬ ልጀምር አይሻልም?
አሁን ይሰማል?
ያ የክብሩ የሚለው ጋር ሄደ ስታወራ ይሰማል፣ ግን ኤኮ አለው ማለት ሌላ ማይክ ኦን ተደርጓል ማለት ነው። ሰምሃው እኔ ጋር ይታየኛል።
እዛ ያለውን የሚቀጥለው ነው።
ሜቢ የቲቺንግ አሁን ይሻላል። ኦኬ አሁን ይሻላል።
አይሰማም ዶክተር?
ይሰማኛል፣ ኤኮ አለው። በጣም የሚያስተጋባ ነገር አለው። ኦኬ ያ አይ ቲንክ ተውት ላሁኑ እንደዛው። አሁን በቃ ሚውት አድርገዋል። አሁን ሁሉም ሰው ሚውት ሆኗል። ስለዚህ ዝም ብለን ክላሱን እንቀጥለው። አይ ቲንክ በኋላ መደማመጥ ስንችል እናወራለን። ይሻላል ይመስለኛል። ኦኬ ኦኬ ሆፕፉሊ ስላይድ ይታያችኋል። ስለዚህ ስለ ሳምፕሊንግ ነው ትንሽ የምናወራው ዛሬ። ፓርቲክል ሳይዝ ዲስትሪቢዩሽን እናወራለን ብዬ ነበር። እስቲ ጊዜው ካላለቀ ሁለቱንም ከቨር እናደርጋለን። እንዳልኳችሁ የምጠይቃችሁ ጥያቄ በኋላ ምን ያህል ክላስ ቀርቷችኋል የሴሜስተሩ ለማለቅ እና እንዴት ነው አኮሚሌት የምናደርገው የሚለው እናወራለን በኋላ። ኦኬ አይ ቲንክ ስለ ሳምፕሊንግ ሌላ ኮርስ ላይም እየወሰዳችሁ ያለ ይመስለኛል። የሆነ ፖስት ካረጋችሁት ያየሁት ሳምፕሊንግ ቲዮሪ ሌላ ኮርስ ላይም እየወሰዳችሁ ያለ ይመስለኛል። ግን ሞር እኔ የማወራው ከሚነራል ፕሮሰሲንግ ጋር የተያያዘ ነገር ስለሆነ ብዙም ድግግሞች ምናምን እንዳይመስላችሁ። ድግግሞች ቢሆንም ችግር የለውም። ያው በተለያየ አንግል አንድ ነገር ማወቁ ችግር ስለሌለው አም አዌር እንዳላችሁ ሌላ አይነት ከሳምፕሊንግ ጋር የተያያዘ ሌላ ቶፒክ ከቨር እያደረጋችሁ አውቃለሁ። ግን ዛሬ የማወራው ሞር የኔ ስፔሲፊክ ነው ከሚነራል ፕሮሰሲንግ ጋር እና ሚነራል ሳምፕልን እንዴት ነው የምናደርገው የሚለው ላይ ነው። ብዙም ዲቴል የለውም። ስለዚህ should be all good. Okay, so probably you are all aware when we say sampling, what we're looking for is a very small portion of a bulk material. So sampling can be done for anything, but specifically here what we're talking about is rock samples, okay? And even from rock samples, specifically we're talking about a rock that has been just mined, maybe after blasting, that has come into a processing mill. And the sampling methods that I discussed today are mainly in relation to that. It's not about sampling to do with resource estimation, sampling to do with geological exploration and other things. It's not about that. It's just specifically about sampling an ore that has been brought to the mill for processing, okay? So this can be just before crushing and grinding or following crushing and grinding, okay? So in any case, what we're looking for is a representative sample, a small portion of the bulk material that we can say represents whatever we have in a stockpile. And usually when we talk about sampling, we talk about a head sample in mineral processing. So the head sample is a sample that's taken for any material that is brought into a processing plant. And we call that a head sample. So a head sample, in other words, can be taken as a feed sample and On a feed sample, you can do a number of assays, a number of examinations, including, for example, we want to determine the grade coming to the mill. Okay, this much gold per ton or this much copper per ton. We want to know the rough sizes of particles coming to the mill. Okay, so this could be 0.5 meter particle sizes or smaller particle sizes, but we want to have a rough idea of size of the particles as well. But typically when we say a head sample, we are using it for quantifying the grade of the material that's coming into the processing mill. Okay, so why do we do sampling, at least from mineral processing point of view? Because we want to take a small amount of whatever we have to process in a mill. So you can take a small mill, for example, or a small processing plant, maybe treating, say, 300 or 400 tons per hour. Okay, so 300 tons per hour comes continuously to the processing plant. Maybe it's crushed and ground and processed. And obviously, we want to control what's coming to our mill. So we can't take 300 tons and do assaying on that. It's just too much of material. It's not economic. It doesn't make sense. So what we want is only a small fraction of that. So in this case, sampling is very critical in order to obtain only a small fraction of the bulk material that's coming into our processing mill. And it can be done for a number of reasons, for quality control purposes, to optimize the processing plant, even to get a rough idea of distribution of particle sizes and a number of other factors. So depending on plant that you're actually operating, you can actually do sampling for a number of purposes. I'll probably more focus on the techniques we use in this lecture today, and you can use either manual sampling methods or you can use automated sampling methods when it comes to processing plants. Okay, so I'll go through some of these examples. So in grab sampling, maybe you have a pile, okay, a pile of rock. Could be 1 million ton of rock, but you want to know how much grade you have in that material, okay, or how much value, economic value you have in that material. So you can use grab sampling by simply taking small portion of samples from different locations on that pile, and then take that and then do assessments on it. Okay, maybe you can use a shovel, okay, take a shovel from here and there from different locations, or you can use a bucket, for example, put the rocks in a bucket, maybe take hundreds of those buckets, and again from that you can work. So instead of, say, dealing with 1 million ton rock, we're trying to somehow narrow that down into maybe 100 grams or 200 grams, or sorry, 100 kilograms or 200 kilograms. And we take that 200 kilogram and we can conduct whatever assessment we want to conduct on. But by grab sampling, we want to take at least samples from different locations, maybe at a fixed interval. If it's a belt, for example, if a sample is going on a belt, we can grab samples from, you know, different locations on the belt at different time intervals, and that can be taken as a way of sampling. But as you can imagine, this is not really an accurate way of doing sampling. It will be significantly based on who is taking the sample. So there will be a large bias associated with sampling. And of course, there will be significant error associated with sampling. But still, to this day, people use it, okay? Especially when you go to, you know, places where people process different type of ores, they still use grab sampling as one method, although we know it's not very accurate. It's cheap, it's simple, sometimes it works, okay? But from practical point of view, it is not an accurate way of doing sampling. Another method is what we call cone and quartering. So as the name implies, if you give me 1,000 tons of rock, okay, maybe it's a pile, you can start with making a cone. Maybe you use a big bucket on a big machine and try to make a cone, like a cone-shaped pile. And what we do then is we flatten the top of the cone, okay? And then we split that cone or that pie into 4 sections. Okay, so quarter means, so as the name implies, we're doing a cone, and then we quarter it, we split it into 4. And then what we do is take 2 opposite sides and discard 2 opposite sides. As you can see there on the picture, we discard the half material, and then we take half of the material, make a new cone with half of the material, and split that into 4, and take 2 and discard 2, and continue until we have the desired size. Okay, so in this case, maybe my desired size could be 100 kilograms. So you need to do continuous splitting and combining and splitting and combining until you get to that final mass, and then that's when you stop your sampling. As you can imagine, this is a lot more random, so it gives you a lot more accurate sampling, and therefore whatever sample you get from this tends to be a lot more accurate compared to just grab sampling. And in terms of where we use it, this is very common in many mineral processing labs. Okay, so if I say, okay, go and please do analysis on this amount of sample, maybe I send you 500 kilos. As I said before, you can't probably say 500 kilograms of rock. It's just a lot of money. It's going to cost you a lot of money, and it's going to take a lot of time. So rather what we do is, for example, we can apply cone and quartering method. And from that 500 kilos, we can split, combine, to maybe 50 kilos. And maybe you can work on the 50 kilos and conduct whatever assay you want, okay, on those smaller portion of material. But in any case, this can be easily conducted in a lab, in a mineral processing lab. Riffle, or riffling and splitting, is also another sampling method. This is probably more common in mineral processing lab rather than actual processing plants. Okay, so from practical point of view, we use this more commonly in the lab, where again, maybe the purpose is to have a quality control done on a processing plant. So maybe they want to know the head grade every day, so they have to take samples every day, and they have to assay that and determine the grade of whatever is coming into the processing plant. So in this case, you can divert a portion of the sample and then use a riffle. As you can see there, I don't know if it's clear, but the riffle splitter on the left has diversion chutes where you feed the sample from the top, as indicated by the arrows there, and then the sample is diverted into left and right. So the sample is randomly distributed and split into half. Okay, so you take one half, continue the splitting again, and discard the other half. Okay, then you take the half, continue with the ripple splitting, split it into half, and again take half, and then discard the other half, and you continue until you get the desired mass. And that can be automated. So the picture you see on the right, the scheme you see on the right there, is a situation where you can actually have a number of containers. In this case, maybe you can have 12 containers which are continuously rotating, okay, on a stage, and you feed it from the top. So you have a feed hopper where sample is fed, and these containers continuously rotate. It means now you're distributing the rock sample on each of those containers. So basically you split it into, say, 12 roughly equal portions. Then you can take that and discard 6 of them, and then take the 6 and then again do it again and again until you get the desired size. So as I mentioned, these are mainly lab-based methods, but they are far more common, and we use them commonly for sampling purposes. Okay, so the other example, instead of using sampling manually, you can actually use automated or mechanical sampling methods. So in this case, with automated methods, you just have to find a way of diverting a fixed amount of material into your sampling chamber. Okay, so you have, say, something that's falling, free falling stream, or maybe something that is in a pipe, okay, or something that's flowing on a belt. The idea will be to cut the whole stream, okay, maybe for 5 seconds, cut the whole stream from a pipe, or divert the whole stream from a belt, and then do that for 5 seconds, and then you let the other material pass through. Maybe after half an hour, you come back again and divert for 5 seconds for the whole stream, and wait another half hour and then come back and do it. So you have a fixed time, but sampling done by cutting the whole stream. And these are usually ideal if you have a slurry, for example, going through a pipe. Okay, you can divert all the slurry from a pipe into the sampling section. Say do it for 5 or 10 seconds, and then release it again, goes through its normal path, and then come back at a fixed time and then divert it again. So it can be done very well for a slurry passing through a pipe, or as I said, for something that's going over a belt. So one of the critical things we want is we want to cut the whole stream, not just say the center or the outside of the belt. It has to be cutting the whole stream so that we get everything onto the sampling portion. And sometimes when the sample cutter moves, if it goes in non-right angle to the pipe or to the belt, it may not give you a nice distribution of the particles again. So you want to be also cutting it at a right angle so that you divert everything without any bias. And usually the cutter is allowed to go or move into right angles to the stream. And if you're sampling big rocks, okay, and your sample cutter is small, then it may avoid sampling the bigger rocks because the bigger rocks will be heavy to be cut by a small cutter. So what you want is, in that case, you at least need the cutters to be bigger than the large rocks, okay, so that they can be diverted. And the thumb of rule is that you have at least the cutter width should be 3 times larger than the largest particle or the largest rock that you are trying to sample, okay? But there are a number of methods or equipments that we use for sampling using automated methods. For example, the resin sampler, as you can see here on the scheme there, is typically used for sampling pipes. Okay, so the pipe or the slurry goes through a bigger pipe, as you can see in the yellow arrows there, the big yellow arrows. Okay, so that's the normal stream of the slurry. But what we can do is we can put a revolving cutter inside that pipe. And basically what it does is blocks the whole pipe and diverts the pulp that is going through the pipe into one portion. Okay, so as shown there in the white arrows, so it cuts and diverts the whole stream into the side, and then diverted that into the sampling chamber. If that is a reasonable sampling size, then you can stop it and you can divert the same amount of material. If you want to reduce the sample further, you can do another stage of sampling again. From whatever you have diverted, you can then cut a small stream and then release the other stream. So in this case, in that image I'm showing you there, you're actually doing sampling twice. First from the whole big pipe, cutting the whole stream, and then take it into a small sampling chamber and cut it again. And the one shown in red arrows there will be the sample you'll be collecting. Okay, maybe in this case you're looking at 100 meter cube per hour flow rate. Maybe what you want is 1 or 2 meter cube an hour to be sampled. Okay, so maybe it's 1% or less than 1% of whatever goes through the pipe is what we're trying to sample. And that can be done by cutting the stream at fixed time intervals. Belt sampler or transfer sampler works pretty much in the same way, except instead of having a pipe and a slurry, we use it for material that moves on a belt. Okay, as you can see there, on the right, you have a belt, and the cutter goes across the belt, okay, right angle to the belt, and it diverts the whole rock that was on the belt for a small fixed time interval, diverts the sample,
and then the material on the belt continues as normal, and then come back again at a fixed time and divert the whole stream, and then do that continuously. So as I said, the cutter or the sampler needs to go and cut the whole stream, because, for example, if you look at a belt, it's possible that fine particles will segregate to the bottom of the belt. Because they're fine, they can make their way through, and then they tend to be on the belt. And therefore, if you're just scrapping the top, chances are you will probably end up just sampling the coarse particles. You'll be missing the fine particles. So you need to make sure that the cutter goes all the way deep to the belt surface and cuts the whole stream there, so that you can get all those fine particles as well. So in practice, again, as I said, sampling is very challenging in many mineral processing operations, because what you have is, say, a freshly mined ore, and you have maybe 1 million tons sitting somewhere as a pile. Okay, so it is not very easy to actually get into all the positions in that pile. Chances are you probably will just focus on the outside of the pile. And usually when you have a pile, the fine particles tend to be on the top of the pile, and the coarse particles tend to go to the ground, and to the base of the pile, you have coarse particles. So even to start with, distribution of the particle will be different in terms of particle size, for example. So you need to be very careful in terms of how you sample it. One of the projects I had with the local mines was, for example, to sample a 50-ton material. What we needed was only maybe 1 or 2 tons of a sample to work on, but we asked them to prepare 50 tons for us. And the material I want is just after crushed. Okay, so I wanted a freshly crushed rock, not the freshly mined, but it has to go through a crusher for me to be able to use it. So we told them, you can crush it, but when you sample, you need to make the sampling applying the appropriate sampling theory. So in this case, for example, as you can see there, we have the crusher on the right. So the crusher crushes the material, and then we have a bobcat or an IT here that is going in and cuts some stream from the crusher, and then samples for a few seconds, and then retracts back, and then the crusher will operate, and then we go back again and do the process. So I'm hoping the video works. Just let me know if you can't see it. Okay, so I hope you can get the idea of what we're trying to do there. So the crusher is crushing and there's a whole stream of rock is falling from the crusher. So what we're trying to do is not take a small portion, but the IT has to go all the way and cut the whole stream. Okay, not just small portion of it, but the whole stream for a fixed time, depending on how much sample you want. And then we want to continue doing this. So instead of just, for example, if I had a big pile and I just go and take one scoop randomly from one position on the pile, it's a lot more better to get representative sample if you had to do it through intervals like this, because at the end of the day, we take this sample and we work on it. So we do, for this particular case, we're just trying to see the potential of coarse gang rejection, okay, like an OR sorting method, whether that gives a reasonable beneficiation or not. So if I was working on the wrong material to start with, my results will be almost questionable, because I have been working on not a representative sample, but something that is not. So when you do projects like this, you need to be very careful to get a good representative sample. Okay, otherwise, whatever follows, whatever work we do on those samples will be questionable. And that's why I always say it's very critical to do sampling properly, following at least one of the standard procedures that we have. Okay, so then we also went to another site, okay, for a similar work. And again, when we asked them to do sampling for us, they just took a scoop from one side of the pile, and they said that's our sample. But we said, no, that's not how we want it. So what we did then was we had to go back, and as you can see there, the bigger pile on the top, from that stockpile, we made what we call cone and quartering, as I was showing you earlier. So we had a small bob cut, which splits the first big pile into 4. Okay, so randomly goes and makes 4 piles, as you can see at the bottom there. And then we discard 2 of the piles. We combined 2 of the piles, and then we do that split into 4. And again, we continue the cone and quartering method until we go to about 2 tons from a 50-ton stockpile. And that took us maybe about 3-4 hours. But at least we know we're getting a more reasonable representative sample if we did it that way, okay? Instead of just taking a scoop from one side of that big stockpile, okay? So again, you can apply this in different ways, but at least you need to follow certain procedure. And as I always say, you need to also give sampling method a very critical attention. Otherwise, whatever generated from that can be very misleading, and it can be very costly at the end of the day. So when is an ideal time for sampling? So usually when we do blasting, or when we did the mining in first stage, we produce fine rocks, we produce very large rocks. Maybe some of the rock is over 1 meter in diameter. And some of the rock is very soft, so it disintegrates and forms a fine powder. So obviously, if I say, okay, go and sample this material, it is going to be very dodgy to start with, because you have fine material, you have coarse material. Maybe some of the samplers may be biased and pick the larger rocks, depending on what method you used. And some of the samplers may maybe bias themselves towards the fine rock. Okay, so either way, it may not be representative. So what you need to do when you have something like this is you need to crush the rock into smaller size particles so that you get a nicely uniform distribution. So stage sampling simply refers to the process of crushing and grinding the rock to a smaller particle size before you start sampling. Okay, so once you produce smaller sizes, then you can now apply any of the methods that we discussed earlier to sample the material. So again, managing the particle size, especially making it smaller, will actually help in accurately sampling compared to, say, trying to sample something that is really large in particle size. And maybe the other question is how much mass is considered ideal. So if I say, for example, you guys go out there and I have, say, 1 million tons of rock that I want you to sample. And in that 1 million rock, I want to know how much gold might be potentially there. And I say, go and sample and do assay and tell me what the rough grade is. Obviously, the first question you ask is, how much sample do I take? And of course, what sampling method am I going to use? So if I ask you guys, is 50 kilos out of a million a reasonable amount to sample? Or would you say 100 kilos? Would you say 1 ton? Would you say 100 ton of a million? So you want to know roughly, how much you want to take, so that you can say you can do your assessment and tell whoever is asking you to have an idea of what is in there. So there's always a question of sampling mass. Okay, how much mass do we need to take from a given stockpile or from a given deposit or whatever the case may be. So people actually try to work out the impact of sampling mass, okay, on error. Okay, what's associated with sampling a small amount versus error associated with a large amount. And they tried to simulate the process. So what they took was they took a hypothetical ore, and this ore has 50% valuable and 50% gangue. Okay, and they sampled the ore or this material 100 times. So they took 100 samples from it, and then they assessed what is in that 100. Okay, of the 100 samples you took, what is the associated error with it. So for example, if you took only 10 grams 100 times, so I take 10 grams of 100 samples, or 100 samples weighing 10 grams. And then what they worked out or simulated was that the mean assay for this small amount of mass would be about 46.7. And the relative standard deviation was considered to be about 88.5%. So significant amount of error if you had to take just 10 grams. When they took 100 samples weighing 100 grams, the mean assay is close to 50. As I told you, 50 is the valuable mineral, 50% is the valuable mineral composition. So 100 grams gives you a close number to that 50, 49.7 is what they got. And the standard deviation was about 45.6%. As they gradually increased the mass of the sample, as you can see there, from 10 grams, it went to about 10,000 grams or 10 kilograms. The assay is very close to 50, and the standard deviation is about 5%. So what that shows, theoretically at least, what they were able to show is as you increase mass of the sample, your error reduces. Okay, so in other words, if I had, for example, 1 ton of rock to be sampled, if someone took 500 as a sample, 500 kilograms of the 1 ton, which is half of it, you probably would end up being more representative as you take more and more of the sample, compared to someone who took only 1 kilogram out of the 1 ton. Okay, because as you increase the mass of my sample, the error associated with it will be smaller and smaller. So that's why we always ask the question of, then we know the mass of the sample is critical, and therefore we need to know roughly how much we need to take from a given stockpile. And that has been calculated by a person called G. Okay, so what he was trying to calculate was for a mass or a stockpile of gross weight of L, okay, can be L grams, okay, maybe a million, a billion grams. What he was trying to calculate was the minimum sample required for a corresponding associated error that can be given by the variance or the standard deviation S. Okay, so what the equation says is the mass, the minimum mass required for a sample, multiplied by the bulk or the gross of the material to be sampled, can be corresponded to the particle size, D, of the particles that I'm trying to, off of stockpile, I can work out the rough sizes of the particles to be sampled. I can associate that with a sampling error and some sampling constant that somehow takes into account the material I'm trying to sample. Okay, if it is a coal sample, or if it is a gold ore sample, or if it is an iron ore, okay, depending on the nature of that stockpile, you can actually try to account and incorporate some estimations to get your error to a low value. So that C there, or the sampling constant, is actually a consideration for the nature of the material to be sampled. Or what we're saying is, if I have a pile of sand, okay, and a pile of very fine rock, and a pile of very large rocks, I can't just use the same method and the same theory to sample them. In this case, I need to account for how homogeneous the sample is, because if your sample is homogeneous, chances are you have very small error. If my sample is heterogeneous, if I have fine particles, very large particles, intermediate particles, and I'm trying to sample that, chances are I will have a large error associated with it. Okay, so that C is trying to account for some of the variation in the material to be sampled. So we're trying to somehow minimize the error associated with sampling by taking into account the nature of the material we're trying to sample. So I'll talk about C in the next slide. So C will have factors corresponding to liberation, shape of the particles, even the size distribution of the particles, and so on. Okay. So in any case, if, as I said in my question earlier, if I had 1 million ton, okay, as a stockpile, the L will be the million ton, right? Okay, so that's what you're going to go and sample. 1 million ton is L. And I was asking you how much mass of sample would be enough to say it is representative. And in this case, what I'm asking you is the M, okay? I've given you 1 million ton of rock stockpile and asked you how much sample is enough to say representative, so that's the M. So usually the M is very small compared to the L, because the L is 1 million stockpile, 1 million ton, but typically what you want might be 200 kilos, the M, okay? So because there's such a big gap between those two numbers, that term L minus M may be just approximated for L, because 200 kilograms subtracted from 1 million ton is actually nothing, okay? So I can just approximate L minus M as just L. If you did that, you can simplify that equation into the one shown in the bottom there. The minimum sample mass required, M, is just dependent on the nature of my sample. In this case, when I say nature of my sample, I could be talking about how homogeneous it is. I could be talking about whether I have very wide particle sizes, small, intermediate, and coarse. I could be talking about the content, okay? So what is it composed of, okay? Is it very high grade? Is it very low grade material? All these factors. So C stands for that. D is the largest particle sizes in my stockpile, okay? And S there is the standard deviation. And therefore, if I have those, I can actually work out the material that is required, or the sample that's required for a given stockpile. So already you can see it's actually immaterial whether I have 1 million ton of stockpile or 100 million stockpile. It doesn't really matter. The L doesn't really matter in calculating the sample mass required, okay? What is more critical is not how much stockpile, it is actually the nature of the material itself, Okay, so that's what that equation shows there. So if I wanted to, of course, increase the chance of getting my sample accurate, or if I wanted to minimize the error, I need to get more M, okay? So in this case, I can play with the S, which is my error. I can make it smaller and smaller and smaller. If I make the S smaller, then that equation tells me the M needs to be large, okay? So in this case, you can increase the mass of the sample to get a small error. Or if you were to decrease the size of the particles, okay, then again, the smaller size of particles can also correspond to smaller errors as well. So when you reduce the D, the S also should reduce for a constant M. So again, as I wanted to reiterate, eventually, what is critical is not how much stockpile I had. What is critical is the nature of the material that I'm trying to sample. So in terms of the C, I mentioned C is my sampling constant. So it takes the shape of the rock, for example, okay? If I'm trying to sample spherical rocks, if they're round rocks, then I can take that factor to be 0.5. If it's actually a bit elongated and flat, then I can give it a factor, F of 0.2. And G is particle size distribution factor. Again, the stockpile may be made from a sand. If it's sand, chances are the particles are very close in size with one another. So I don't get extremely large sizes and I don't get extremely small sizes for a sand. The sizes are very comparable, okay? This is a narrow size distribution, which means in this case, my G, the G value will be about 1. But if there are very large rocks and very small rocks, then the value of G would be lower. In this case, for example, 0.25 is given if the top large particle sizes is divided by the small particle sizes, and that factor is more than 4, then you can take the G value to be 0.25. In this case, what we're saying is there's a very big gap between the smallest particle and the largest particle in terms of size, okay? Or you can have something in between the extremely, between the 1 and the 0.25, and you can take a factor of 0.5 and so on. Again, all we're trying to say here in terms of G is it is also useful to take into account the particle size distribution of the material I'm trying to sample as well, okay? Because already I know if the stockpile has uniform particle size, error associated with size is very minimal. If the stockpile is made from very wide size distribution where you have fine and coarse particles, error associated with that will be very high. And L is the liberation factor. So it goes from 0 to 1. Again, if it's completely homogeneous, L would be close to 0. If it's completely heterogeneous, then L will be close to 1. Okay, but usually L will be somewhere between 0 and 1 and can be calculated if you know, for example, the size at which you can totally liberate the material. You can divide that by the top size, okay, to obtain the value of L. So what's left there is the M, okay, and M is what we call mineralogical factor. So again, we're trying to account for mineralogy as well, okay? So in this case, it is different to sample something that has, say, 70% valuable material in it compared to something that has 7% valuable material in it, compared to something that has 0.7% valuable material in it, okay? So we're trying to account for the fact that the nature of the sample and the mineralogy of the sample can also play a role in somehow introducing error during sampling. So again, in this case, M is given by that expression there. So A is the mineral content of the material. Okay, so it could be, for example, if it is made from 2% chalcopyrite. Chalcopyrite is the main mineral. So the fractional value there will be 2%, which is 2 divided by 100. Okay, so that's what is D referring to. And R is the density of the valuable mineral, so the density of chalcopyrite, for example. And T is the density of the gangue, maybe density of quartz. So you can take that into account as well. Okay, so you can further simplify that. If A is small, if it's a low grade ore, maybe you can just simplify the value of M and calculate it there. Okay, so I know now it is becoming more complicated. So I'm sure when you guys thought of sampling, you would think it shouldn't be complicated like this, as long as you take, the proper sampling method. So all we're trying to do here is actually factor in what we know about the material to help us get a more accurate sampling, okay? So obviously it's not something that has to be strictly followed, but it's something that you need to appreciate when you do sampling. It's not just okay to take a sample using the same method, okay, when you're trying to sample different types of materials, okay? So in this case, if I ask you to sample a sugar, okay, compared to say, even salt with very different particle sizes, compared to sand, compared to a quarry that you want to make road with, compared to an ore particle. So all these have some variations, although they're probably rocks or solid particles. You should probably account for some of their properties and minimize the sampling associated with them, and therefore that will give you a better chance of obtaining a representative sample at the end of the day. Okay, hopefully that sound issue is resolved, and I'm hoping maybe some of you have questions, so maybe I'll just pause a bit and see if you guys have questions. Any question? No? Okay, so for one of the practicals, hopefully they will be able to demonstrate sampling techniques for mineral samples. So in this case, you are going to perform a few examples on how you can do, for example, the riffle sampling if you have the riffle splitters in the lab there. Hopefully you can do cone and quartering, you can do grab sampling and pulverizing. Okay, and at least when you do the practice, hopefully that starts to make sense. But as I said, so this is all about trying to minimize error and trying to appreciate for the nature of the material you're trying to sample. So if you guys don't have questions, maybe we'll just do one exercise here, okay, just as a refresher. Okay, I understand that there's a lot of information there. Maybe you guys could be overwhelmed by it. So it's just dependent on what we've just discussed earlier. So what we're trying to find is the minimum sample required, okay, which is the M, that's what we want. And in this case, the original stockpile is not even mentioned. So the L, which is initial pile that we're trying to sample from, is not mentioned. And as I said, it's not really the critical factor. So whether you have 100 ton or 1 million ton or whatever is not really the critical factor here, okay? What is critical is more to do with the nature of the material itself, okay? So you probably will need to find all those informations that are shown earlier. So we have the D. The D here is given, the top size is what the D is. So the top size simply represents the largest rocks. So the size of the largest rocks in that pile, okay? And that is given as 2.5 centimeters. And also you're being given the liberation size. So this is the size at which the mineral is expected to be liberated. And that's given as 75 micron, which is the H. And you can convert that into centimeters. And that's what you should get, 0.0075 centimeters. Okay. The other information you would need is to calculate, for example, the M, the mineralogical factor. You will need to calculate the A, the R, and the T, or you need to determine A, R, and T. Okay. To determine the C, which is the sampling constant, you will need to work out F, G, L, and M. Okay. So on that left side, we're just trying to determine those. So the R is probably straightforward. So R here is the density of the valuable, or in this case, the valuable chalcocite, which is the copper mineral. Okay, so density of the valuable mineral is given 5,600 kilograms per meter cube, sorry. And the T is given there as the density of the gangue, okay, as 2,500 kilograms per meter cube. Probably what is tricky is to work out the A and the S. Okay, F and G are given, so there's nothing to do there for shape factor and size factor. So we can use those values there. So to calculate the A, if you remember, the A is used to calculate the mineralogical factor. And I told you that is the fraction of the valuable mineral. Okay, so here the valuable mineral is chalcocite, but its fraction is not given there. What's given is the fraction of copper, and the copper there came from chalcocite. Okay, but chalcocite is not 100% copper. Chalcocite is made from 2 copper atoms and 1 sulfur atom. So what we need to do is, if the copper is 9%, then what will be the chalcocite percent in the material? Okay, so all you have to do is then rely on the molecular weight or the atomic mass of the copper and the sulfur, and you can, based on that proportion. Okay, so for example, based on atomic masses, out of 159 chalcocite, 127 is copper. Okay, so now I know copper is 9%. What is that corresponding to for chalcocite? You should get about 11.3%. Okay, I hope that makes sense to you guys. So now I know the percent of chalcocite as a fraction. 11.3% is 0.113. Okay, so mind you here, We're not taking the fraction of copper, we're taking the fraction of the valuable mineral in the ore. Okay. For the S, I told you S is the standard deviation, or if you take S squared, that's the variance. But what's given here is the confidence level. Okay. So we need to sample it with a confidence level of within 0. Plus or minus 0.1% of the copper. So we know the copper is 9%. We need to know what is 0.1 of the 9, which is copper. Okay, or 0.1% of the 9%, or 0.1 of the 9. Okay. And if you did that, then you will calculate the S to be about 0.00555. So now you know all the necessary values. So you say, using that earlier expression, M, which is the mass required, or minimum sample mass, is given by capital C d cubed divided by the S. Okay, S squared. And therefore, in this case, I know the C can be calculated from F, L, G, and M, which are all able to be determined based on those values. And the D is given there, the top size, which is 2.5 centimeter cube. Okay, so again, you need to be careful in terms of units. So the density is given in meter cube, either convert that into centimeters or convert the sizes, okay, into meter, whichever way. So the D can be expressed in meter, okay, or the density can be expressed in centimeter cube, whichever is suitable. So if you do that, then that's what you get. So M can be calculated based on those expressions, and the liberation factor can be calculated based on that formula, and the C can be calculated, and M can be calculated. Okay, so what we're saying here is to get our sampling with accuracy within 0.1% of copper, you need to take at least about 130.6 kilograms. If you take more than that, then you will be within that error. Okay, if you take less than 130, you probably would have more error associated with the sampling, okay, other than what's allowed. Okay, I'm not sure if whatever we did makes sense to you guys, but feel free to ask questions so that we can maybe discuss some of the points. All good? Okay, nobody's saying anything. Okay, I don't know if you guys are trying to say something, but I can't hear anything. All good? Okay, so since I can't hear much, I will probably go to the next topic, and we'll do a similar exercise later on. So you can probably ask questions if you have any. Okay, but I can't hear much from your side. Okay, so I am on to the next topic. I hope you can also see these slides. So we're going to be talking about particle size distribution analysis. Okay, so I mentioned this every now and then during our course, but we'll probably do it properly today, as this is also part of a proper activity in any processing plant. So you need to probably do your particle size distribution analysis properly. So again, I'm not sure if you're going through a similar topic in another course, but I'm pretty sure this is more specific to what we're trying to do in this course. So again, it might be slightly different from other courses where they talk about particle size analysis as well. Okay, and I will do an example later on for this one. And I don't know if you guys managed to print some papers that I have shared with you guys on Telegram, but if you haven't, that's not a problem. But I'll just do an activity later on. Okay. Okay, so why do we need to do particle size analysis or particle distribution analysis? It is very important because, again, typically in this course, we're talking about crushing and grinding. Okay, so the only way you can tell the efficiency of crushing or grinding is only if you know particle size distribution before crushing or before grinding, and particle distribution after grinding or after crushing. Okay, so every time you crush something, you need to know the starting particle size, and you need to know the product particle size to assess the performance. If you don't have that information, if you don't have particle size distribution for the feed, if you don't have particle size distribution information for the product, you're just blindly doing grinding. Okay, maybe you are hitting your target, maybe you are not. So there's no way of knowing the efficiency of the grinding operation, right? So that's why you need to keep an eye, or at least determine quantitatively the distribution of the size of particles in the feed and that of the product. Okay, so one reason for doing particle size distribution is to assess performance of a milling operation. But another critical factor is usually you grind the particles to a certain size, and then you feed those particles to the next processing operation. So in this case, it could be a gravity separator following grinding, or it could be flotation following grinding. And usually those processes are very specific in terms of what particle size range you can feed into them. Okay, for example, gravity separators are more suited for coarse particles, and flotation is more suited for fine particles. So again, once you grind, you need to control the particle sizes going into flotation plant, or you need to control particle sizes going into a gravity separator. If you don't control that, chances are you probably will affect the performance of that process. Okay, so if you're feeding flotation with coarse particles, then the particles are too heavy, they don't float, you lose the valuable commodity. Okay, so that's very critical. So we need to control, one, of course, the performance of our processing plant, but also we need to control what goes into the next stage processing. Okay, so the other factor is, of course, we are saying this because when you feed particles into a processing plant, the size of those particles determines how they move inside that processing plant. Okay, if you're feeding just coarse particles and you're using a typical gravity separator, coarse particles move very easily, okay, in that separator. Fine particles are a lot more challenging to move because we usually mix it with water. Fine particles tend to be very thick. They produce a thick pulp, a viscous pulp, while coarse particles are easy to move around in the processing plant. And therefore, that actually significantly affects the performance of the processing plant. Okay, so that's why we need to do particle size distribution, at least from mineral processing point of view. If we're making rods, it's a different story. Okay, if I'm making gravel or whatever for making rods, what I want is produce uniform size particles, okay, and probably of a certain shape. It could be mainly a spherical or a square shape particles. So those are different requirements. So we're not going to talk about those, especially when I discuss this topic here. We're more focused on processing and mineral processing operations. Okay, so now I give you, say, 100 kilo of rock. I say, please go take this sample and mill it using a laboratory ball mill. And I say, then determine the size of the particles before and after. So when you obviously grind it, you're not going to make spherical particles. You're not going to make perfectly rectangular particles or cube particles. Chances are you're going to make irregularly shaped particles all over the place, and could be fine, intermediate, coarse. So when you assess particle size, what is the key thing you'll be looking for? Because if I gave you an irregularly shaped rock, how do you give me the size of that rock? Okay, do you just take from one side to the other side and then just measure that and give me the length of the rock? Or is it more the diameter of the rock? Or do you just take the diagonal across it? So how do you actually measure a size of a particle? That's one of the challenging things we have, okay? Because if I gave you a ball, you can just take the circumference of that and you can give me the diameter or the radius of the ball, and that would be the size, okay? I can say this is the diameter of the ball, which is easy to determine. If I gave you a cube, then you can just measure the height of the cube and tell me this is the size of the cube. And probably the same for a rectangular shape. If it's perfect rectangular, you can give me the length or the width of that rectangle. But if it's an irregularly shaped rock, how do you then measure its size? Okay, so that's one of the challenge we have in determining particle size, because when you put a rock in the mill, it will randomly break and it will give you all different types of shapes, okay, very irregular shapes, and measuring the size of those will be very difficult, because theoretically you can't measure each and every particle and give me the sizes. That's simply impossible, because if I give you 1 kilo or 100 kilo, you produce millions of particles. And there's no way you can sit down and determine the size of all those particles. It's just not practical. So we need to have a way of measuring particle sizes. So because we're not really communicating well, I would probably just go, I was going to ask you questions and see your thoughts in terms of how you think we can do this, but I will probably just go to the next slide. Okay, so in this case, diameters of spheres are easy to determine, or cubes are easy to determine, but irregular shaped particles are more challenging. So if you look at that slide there and just look at the irregularly shaped rock, do you think the maximum diameter is what we're looking for to determine the size? Or do you think it's the smaller diameter actually? It's not really clear, is it? You can actually use either, but there are other ways of determining particle sizes. So in this case, even if you use the minimum or the maximum diameter, from practical point of view, it's not possible to determine the size, the maximum diameter or the minimum diameter for all individual rocks, okay, from a given powdered sample. So what we use are different methods, okay, or estimations to come up with a good representation of particle size. For example, one of the most common thing we do is to determine the smallest sieve aperture through which a particle passes. Okay, so you have a sieve which has same sized holes on it, and you put the milled rock or milled powder on that sieve, and then you give it a good shake. If particles pass through that sieve, it is because they are smaller than the aperture size. Okay, then we can say I've taken 1 kilo of rock, maybe milled rock, and half of it passes through that mesh or that aperture of the sieve. It must be because they're smaller than the smallest opening on that sieve. Then that opening size or aperture size is taken as the particle size. Okay, or the particle size corresponds to that aperture size. That's one way, or one of the most common way of determining particle size. If particle passes through a given aperture size, it's because they're smaller than that size. Okay, so that's one way. Or you can actually play with settling. Now, with settling, we know if you apply Stokes' law, for example, we know particles fall at a certain rate. Okay, if you have a milled rock, put it in water and give it a mix, coarse particles will sink first, and then fine particles will start sinking. Okay, depending on the size of the particles, you have different settling rates. So for a perfectly spherical particle, Stokes' law can be applied to determine terminal velocity of that spherical particle. So let's say you have 500 micron particle that is spherical. You can measure its settling rate. Okay, and then I have another irregularly shaped particle. Okay, if that regularly shaped particle settles at the same rate as this spherical particle, it must be because they have comparable size. Okay, if it settles faster than this spherical particle, then it's larger. If it settles slower, then it is smaller than this spherical particle. So again, we can take what we call Stokes diameter to be able to work out roughly a particle size of an irregular shaped rock, okay, by taking the settling rate of a spherical rock. Okay, something like that. And the other thing you can do is take a small sample, maybe 2 grams or 1 gram from whatever you milled, and put it under a microscope and see the size of individual particles. Okay, individually look at them under a microscope. Now, as I say, they're probably irregularly shaped anyway, but you can try to fit a circle into those irregularly shaped particles. If they fit into a given circle of given diameter, then you can say that particle has this much size because it fits into a diameter of this much circle. Okay, so that if you did that, that will be called a projected area diameter. So you can use either the sieve aperture diameter to determine particle size, or you can use the Stokes diameter, or you can use projected area diameter. But regardless of what method you use, obviously in a given operation, you need to be consistent and you need to apply that correctly. Okay, but as I was saying, by far the most common will be to use sieves or sieving technique to determine particle size distribution. Okay, so what are other methods that we use? Okay, or what are the methods in terms of equipment that apply those previously mentioned principles? It depends on, again, your particle size range. Okay, so sieving is one of the most common because it can be applied to a very wide range of particle size, somewhere from 5 micron to even up to 100,000 microns, so about 100 millimeters. Okay, again, probably not as effective when you're trying to see particles below about 38 micron, even if you use what we call wet sieving method. There will be limitations again. So usually we don't use sieving if particles are below 38 microns, especially the dry sieving method, because we know it's not very accurate. But in many mineral processing operations, the particles we're dealing with are somewhere from about 75 micron to about 500 micron. Okay, and that's within a very good range to apply sieving. And you can do both dry sieving and wet sieving, and that's why it is very popular. You can use laser diffraction, which is an equipment that we use for particle sizing. We can use illustration, microscopy, even sedimentation. And as I mentioned also, you can use electron microscope for very fine particles. So what I will do in the next slides is go through each of these, okay, and probably talk about them a little bit so that you get an idea of how each method works. Okay, so with sieving, as I mentioned, we have different size apertures on each of those sieves. Okay, I don't know for those of you who are not familiar with sieves, but it's probably what our moms use to process a flour before they make a bread or whatever. They want to get rid of some of the unwanted material from flour, and for that they use sieves. And probably what they use is maybe one size sieve, but we can make sieves in different sizes with different openings on them. Okay, so what's critical here is we can make them to have different size apertures to allow coarse particles to pass through or only fine particles to pass through. So we have maybe 5 or 6 of them, from the coarsest one to the finest one on top of one another. And you put your milled material onto the top one. If they're really large rocks, they will be retained on the first one. All the fine ones will pass to the next sieve. And again, depending on the size, some will be retained on the next sieve and some will pass through. And then that process continues to the bottom of the sieve. So in each of those sieves, we'll have some amount of material retained. And therefore, at the end of the day, what we can take is, now I took 6 sieves. I have this amount of material in the first sieve, this amount of material in the second sieve, this amount of material in the third sieve, and so on. And that can give us an idea of the particle size distribution, or how coarse or how fine the particles are. Okay, so usually in terms of progression, we use what we call root 2 square, root 2 progression for sieves. I will talk about that in the next slide, so don't worry about it. So it's just the size of sieves. So we start from, say, 850 or even above that, 2 millimeters and so on, and all the way down to 38 micron, even about 10 micron. And the size of the sieves we use are in terms of geometric progression of root 2, and I will display that in the next slide. And of course, as I said, you can do it wet or dry. And of course, once you put your material on a sieve, you need to give it a bit of a shake to allow particles to pass through the sieves. Okay, so this is all about presenting particles to the sieve so that they can be allowed to be contacted with the surface of the sieve and provided the opportunities to pass through each of those sieves. So shaking is important. So if you retain particles in a given sieve, so that will be represented as plus whatever sieve size you have there. So if, for example, I use 500 micron sieve and retain particles on that 500 sieve, so those particles will be plus 500 micron because they are coarser than 500 micron. If they pass through that 500 micron, they are minus 500 because they passed through the 500 micron must be because they're smaller than 500 micron. Okay, so the plus and minus simply represents for a given size sieve above and below the sizes. Okay. So in terms of the progression, the British Standard Series and the American Series are commonly used. And these are just based on different, slightly different size apertures. For example, for the American Series, this is what's given there. So 850, for example, micron, 600 micron, 425, 300, and so on. So we're just following a root 2 geometric progression from the top to the bottom. So you can go up, okay, in millimeter sizes as well. And you can go down from 38 continuously as well. So, but these are usually the standard sizes where we do most of our operation, because typically in mineral processing operation, you just ground the particle. We don't usually deal with particles coarser than 1 millimeter. They're just too coarse to process. So gravity separators don't handle that. Okay. And therefore, somewhere below 850, particles can be processed. Okay. And going down, if particles are below 5338 micron, then again, they're going to be too fine and they're going to be challenging to process. I'm not saying they can't be processed. Yes, they can be processed, but they're going to be challenging to be beneficiated. So that's why that's displayed here. But regardless, I just wanted to display here the possible sieve sizes that you can use to work out particle size distribution. Okay. So again, I don't know, in your lab, you might find the British series, which is slightly different in number here, or you might find the American series, but it's not really important. What is important is whatever sieve you use, that is the size of the aperture, and that's what you need to include in your data or analysis. Okay. And again, I don't have to use all of this. I can use only 5 of these or 6 of these displayed in this slide here. And based on those 5 or 6, I can also express my particle size distribution as well. So don't strictly follow this one, but these are the possibilities. If I have to use, I can pick any of these ones from top to bottom to do my particle size distribution as well. Okay, so that is sieving. The other one I mentioned was sedimentation. Okay, based on how long it takes for the particles to settle, we can find the corresponding size. Okay, and I mentioned Stokes' law. So Stokes' law says that the terminal velocity is dependent on the size of the particle. So in this case, the diameter of the particle, gravitational acceleration, density of the particle, and density of the fluid, and viscosity. Okay, so when we say terminal velocity, so if I have particles in water, for example, particles start to fall initially in water. Now I have gravity pushing them down and the water pulls them up. Okay, so there will be a balance between what is going down and up. So if the gravitational acceleration is high, of course, particles will fall down. And at some stage, there will be a balance between the fluid resistance and the gravitational acceleration, and particles will start to fall at a uniform rate when that equilibrium is attained. And when particles start to fall at uniform rate, we call that the terminal velocity. It is the velocity at which particles fall once that equilibrium between buoyancy or between force of the fluid and gravitational acceleration is balanced out and equilibrated. Okay, so in any case, any particle will have a corresponding terminal velocity. Okay, for a given density of particle and density of fluid and viscosity, I can work out either the terminal velocity first and determine its size, or if I know its size, I can determine the terminal velocity. Okay, so in this case, what we're saying is if I can measure the terminal velocity of some unknown particle size, because I know that terminal velocity corresponds to a given spherical particle, I can then correspond those two and I can work out its particle size. Okay. So again, how do we do this? We can use either a Becker decantation here, for example. That's one of the simplest way of demonstrating how terminal velocity is applied to work out particle size. Okay, so what we do is you don't need any fancy equipment. You can just use, say, a beaker, and you have particles that you want to measure their size. Okay, so what you need to do is, for example, it might be, I'll probably go here. So I might have particles ranging in size from 38 to 850. So I can first maybe determine particles with size of 150 micron. Okay, so those that are below 150 micron, and those that are larger than 150 micron. How do I do that? So I'm just splitting it into two initially, okay? How do I do that? I'll just come here and I say, now, if D here is 150 micron, okay? And now I know some particles are above 150 and some particles are smaller than 150. I want to split them into plus 150 and minus 150. So what I need to do is to calculate the terminal velocity that corresponds to 150 micron. Okay, how do I do that? I can do that by measuring the settling rate of my sample. Okay, so in this case, you just mix the particle, and if I say I have, for example, a beaker with length L, okay, and I have a tube, a siphon tube, which is inserted into that beaker to about 90% of the length of L. So this is H, okay. I have H, which is a tube going not all the way to the bottom of the beaker, but up to about 90% deep into the beaker. So that's my H, and the L is the length of the beaker, which is the total length of the pulp in there. Now I mix everything, let the particles settle, okay? If I determined the terminal velocity here, so in this case here, terminal velocity is given by D, which now I know, so that's 150 micron. I know the gravitational acceleration. Now, if I know what particle I'm dealing with, I know the density. If it is, say, mixed in water, I know the density of the fluid and the viscosity. So in this case, if I have started with a given D, a known D, 150 micron, I will determine V, the terminal velocity. And as you can see, the terminal velocity is given by meter per second. Okay. So now I've determined terminal velocity for 150 micron. What I will then do is for 150 micron, I can calculate the time taken for particles that are 150 micron to sink to the bottom. How do I calculate that? I calculate that because I know H, because I can measure the length of my beaker. I know how deep H is, so H and L are known. Okay, so I know the V, which is the terminal velocity as previously indicated for 150 micron. So if I know H and V, I can calculate the time. So maybe the time comes at, I don't know, 5 minutes. Okay, so for 150 micron, for all particles which are at least 150 micron in size to settle, I need 5 minutes. So what I would do is give it a good mix, let it settle, wait 5 minutes, and then now I know all particles which are at least 150 micron in size have settled. So what I will do is I will remove the top solution, okay? When I remove the top solution, I will remove all the smaller particles that are below 150 micron as well, right? So the one that has settled is coarser than 150 micron. The one that is not settled, it must be because particles are smaller than 150 micron, and therefore I can now split particles into plus 150 and minus 150. Obviously, I need to do this for all other sizes. Maybe I'll go back and I say, okay, now I know I have two portions now. One is above 150, another portion is below 150. Maybe you can take 300. So those that are above 150 micron can now be again worked upon using 300 micron as the D value. Okay, so again, go back here, determine terminal velocity for 300 micron, calculate the time required, and based on that, let it settle. So it must be shorter time than 500. Okay, must be shorter than 500, 5 minutes compared to the 150 microns, 300 micron particles should sink well, should sink quickly as well. So I have now maybe, I don't know, 3 minutes or 3.5 minutes. Wait 3.5 minutes, again remove, coarse and fine. You do that again and again. So obviously this is going to take you a long time and it may not be as accurate. But if you don't have sieves, okay, maybe it's something you can try. Beaker decantation can be used as one way of determining particle size, okay, of a given sample. Okay, I hope I'm making sense to you guys, but if there are any questions, maybe you can ask me later on, but I hope maybe you have an idea of what I'm talking about. Okay, illustration is another method for determining particle size distribution. In this case, what we do is we have our pulp or sample falling from the top, and we introduce water from the bottom, and particles settle against the flow of water. So those particles that resist the upward flow of water will pass through it and will sink. If they're coarse enough, if they're dense enough, they pass through it and settle. Those that can't resist the upward flow of water will be reverted back. And again, based on that, we can split particles based on how fast or how slow they're settling. Okay, and this is just an example of that. I'm probably going to be a bit hurried because I think I'm taking too much time explaining things. Okay, so again, slurry goes from the top and water goes from the bottom. Particles that are coarse will settle against the flow of water. Particles that are fine will go to the next sorting column, and then again we do the same thing in the next column, but in this case the velocity of the water going upward will be reduced, okay, so that we allow smaller particles to sink and fall through, and then we go to the next chamber. Again, we reduce the velocity of the water going up to allow more finer particles to drop, and by doing that we can actually segregate particles into different size fractions. We'll talk about this one when we talk about classification. Cyclosizer is another example of particle size distribution technique. Again, in this case, as the arrow indicates there, we introduce the feed and we use a number of cylinders which are put one after the other. And as particle or the pulp is introduced to the cyclone, in this case we call them cyclone, it's actually introduced in a tangential motion. So it's introduced in a swirly motion as shown in the left picture there. And usually what happens is, because you have internal pressure inside the cyclone, you have centrifugal force operating. So coarse particles will have enough centrifugal force, so it will be drawn to the wall of the cyclone, and they will make all the way up to the top of the cyclone. Fine particles will have more drag force compared to centrifugal force, so they will be drawn to the middle of the cyclone, and they will exit through the center of that cyclone, as shown in that picture there. So if I have a number of these cyclones, one after the other, I can do the first cyclone separates only the coarsest particles. The remaining particles go to the next cyclone, and we increase the pressure inside that cyclone. Then we draw more particles to the wall. Again, they go to the top. Fine particles go to the next cyclone. Again, I increase the pressure more, internal pressure. I draw more fine particles to the wall, and so on. By doing that, we can split particles into different size fractions, and that's one way of doing it. So the only limitation with this one is usually it handles very narrow particle size range between 10 micron to maybe about 50, 55 micron. It doesn't go beyond that, so that's one of the limitations. So it's usually applied to very specific plants which are working in that size range. And it's an older technology still being used. And hydrocyclones work in the same principle, but I'm not going to talk about hydrocyclones today. We'll talk about them when we talk about classification. Okay, microscopy, basically as the name implies, take a sample, a milled material, put it under the microscope and try to measure particle sizes. And this can be using maybe fitting a circle into those particles and maybe roughly estimating the dimension of the particles. And once you do that, you can present that in a histogram or something like that to work out particle size distribution. So in a way, this can be considered as a true particle size determination because you are actually looking at the particles and determining them. And therefore, that can be a lot more accurate. But we don't use this for daily purposes because it's incredibly expensive. Electron microscopes, in particular, are very expensive. And we can't do this on daily basis. But if you wanted to check something quickly, maybe once in a while, is something we can apply as well to determine particle size. Laser diffraction, I don't know if you have a laser sizer in your lab, but this is one of the most common methods these days to determine particle size. And hopefully, if you have that equipment in your lab, we can do a practical on this topic as well, and hopefully you can use the laser diffraction or the laser diffractometer. But otherwise, I just explained the working principle here. So again, with laser diffraction, what we do is we make a pulp of the particle. So basically dissolve the sample in water and then feed it to your laser sizer. And as particles pass through the machine, you're subjecting the particles to a laser beam. You subject it to a laser beam, and based on the angle of scattering coming from the particles, you can actually relate that to the size, because we know large particles scatter the laser at very narrow angles, okay, but with high intensity, and small particles will scatter the laser at wide angles, and therefore based on those we can actually work out, based on the how wide or how narrow the angle of scattering is, we can actually associate that to particle size. And they put a lot of detectors inside the laser sizer, and those can pick up a very wide range of particle sizes. Theoretically, you can use it for particles as small as 1 micron or less, and you can even use it to particles as large as 2 millimeter. So it can handle a very wide particle size. And it's a very simple process. So it probably takes about 5 minutes to get your results printed out. And this is one of a more advanced way of determining particle size. Okay, so now once you have determined particle size, or once you got the data, how do you then report it? How do you display it? And you can use a histogram. A histogram looks something like this, okay, where you have sizes, okay, from small to large, and then their abundance. Maybe the y-axis can be represented in a percent, or can be represented in number of particles falling in a given size range, and therefore the x-axis can be size or particles, and the y-axis can be either percent or their abundance, and therefore it can be displayed simply in that histogram, okay? But probably the histogram doesn't tell you much, so we're more inclined to use other methods. So one of the things people use as a standard way of determining particle size is to determine the P80, which is 80% passing size. So for example, if you have a ball mill, you could say my product needs to have P80 of 150 micron. So that P80 tells you 80% of the particles are below that size. If I say P80 is 150 micron, 80% of particles are smaller than 150 micron, okay? Of all the particles you have given me, this is the size, okay? So people usually rely on that. So they will simply say, okay, my ball mill operates at P80 of 150 or 200 micron, and all they want to determine is P80 to see the performance of the mill. But probably you can use other methods like the Gordon-Schumann plot or the Rosen-Rammel plot to get a slightly more detailed information about particle size distribution. So let's say you did sieving of all the methods I discussed. Okay, let's say you did sieving, you used 500 micron sieve, 355 micron, 250, 180, 125 micron sieves. And let's say initially in the 500 micron sieve, you retained 0.1 grams. In the 355 sieve, you retain 1.5 micron. In 250 micron sieve, you retain 5.2 grams, and so on. Okay, so that is something you can do. So you take a sample, use those sieves, maybe shake it for 10 minutes. We have special equipment for this. We call it raw tap, for example, one of the more common shaking equipment. So after 10 minutes, I have retained those masses there. So then I want to determine the P80. Okay, so if I wanted to determine the P80 here, I can just rely on this information here. And I can determine the 80% passing size for this given sample. And to do that, all you need to do is, now these, the ones shown in column 3, the mass in grams, is something you can determine by simply taking whatever you have in each sieve, take it to a balance and weigh the sample in each of those sieves. You get that column, and then add them up, add all the masses in each of those sieves. That is 0.1 plus 1.5 plus 5.2 and so on. So that will be the total sample mass. Once you have that, you can express it in percent. Okay, 0.1 divided by the total mass can be given by the mass percent there, 0.3%. And again, you can do the same for the next, so 355, 4.9, and so on. Express that as a percentage, and that percentage can be then given as a cumulative. Okay, so the next columns there, the passing and the retained, are simply either you can take what is retained in each sieve and express them as a percent, or just focus on what is passing. Of the 100%, if 10% is retained, 90% is passing. Okay, so as the passing and the retained are simply 100 minus 1 will give you the other. Okay, so 100 minus cumulative passing will give you the retained, or 100 minus cumulative retained will give you the passing. Okay, but in any case, you can put it in percent. So for example, to look at the first row there, if I say I have retained 0.3% in the 500 micron sieve, it implies that 99.7% pass through that sieve. Okay, so for the 355, if I say I retained 4.9% in the 355, I retained 0.3 in the 500, now I retained 4.9% in the 355. So the cumulative will be 100 minus 0.3 minus 4.9. So that should give you 94.8%. So cumulative adds up from the previous sieve going down, or you can work in terms of retained as well. Okay, so I will do an exercise on this one, so don't stress about it if you're not getting what I'm talking about. Okay, so when you present it, you can present it in linear, so that's distribution in y and size in x, or you can use linear on the y and log scale on the x, or you can use some of the more common methods that we'll discuss as well. So the Gordon-Schumann plot is dependent on passing sizes. Okay, I discussed about passings or percent passing earlier. So that's the P. And the empirical formula we use for this one is P passing size equals 100 by X divided by K. The X is the size of particles on the X-axis, and the K is the size parameter. Okay. So the size parameter here simply tells you the top size or the 100% passing size. And the A tells you the distribution parameter, which can be obtained from the log-log plot of the passing and the particle size. So in this case, distribution parameters tells you whether the particle size is narrow. If all the particles are very comparable sizes, you get a narrow distribution. If particle sizes are very far apart, if you have small and very large particles, then the distribution becomes wide. Okay, so that is the measure or what we mean by distribution parameter. Okay, so if you took that empirical formula there, the first top one, and take log scales, okay, log of P is log of 100 by A, log of X by K. And again, log of X by K can be further broken down. And eventually you will get an equation there at the bottom where the log of percent passing equals A, which is your distribution parameter, multiplied by the log of X, which is the size, plus a constant. So what it says is, if you give me that table there, okay, this table here, and if I took the undersize or the cumulative passing size shown there, okay, on the y-axis, and put it on the log scale, and took the nominal sizes in micron shown in column 2, or the aperture sizes, and put that on a log scale on the x-axis, then that should give me roughly a straight line. Okay, so that's what Gordon-Schumann plot is saying. So now if I plotted those two on log scale, I plot a straight line from the slope, I get an idea of distribution. Okay, and from the K value, I get the theoretical top size or the coarsest particle size. So why do we bother about all this? Because if you go to a processing plant, if you're working in a processing plant, we need to follow a standard operational procedure. So they usually mine for 20, 30, 40 years. And usually the grinding mill, for example, doesn't vary continuously. So once they have a mill, a ball mill, for example, maybe they will have it for 20 years. So the best way of controlling the efficiency and operation of the ball mill is to use a standard method in that processing plant to determine particle size distribution. So maybe a processing plant may elect to use the Gordon-Schumann plot. So every day, you're not going to come with a new particle size distribution method. The method that you use is already given, the Gordon-Schumann plot. That's their standard method. All you need to keep an eye on is the value of A and the value of K. Okay, so from day-to-day data, you get this information here, and you plug this information into your Gordon-Schumann plot. You determine K and A, and if it's within the acceptable range for that processing plant, you continue operation. If somehow the values from day to day continuously increase or continuously decrease, then you need to control and you need to ask what's going on. So that's why we need to follow certain procedure, certain standard procedure, to be able to determine those parameters and then keep an eye on the daily activity of the plant. Okay. If you don't use a standard plot or standard method, then you're just poorly controlling the plant. Anything can happen that you have very little control, or when things go wrong, you have very little control. So that's why this is important to know. Okay, so whether you use this one or another method depends on the specific plant, but at least you need to use a method. So if you used the log of P and log of X, as I showed you here, and plotted that on log scale, you have something like this, okay, where the curve looks very nicely linear initially, but as you go to coarser and coarser particle sizes, it becomes a bit congested, okay, especially above 75% passing. Okay, that's one of the limitations of Gordon-Schumann plot. Okay. In cases where, for example, for your particular mill or for your particular ore, the Gordon-Schumann plot doesn't really work, you can probably consider another plot, the Rosen-Ramler plot, which is shown by this expression here. So again, some people call it the Weibull distribution. Excuse me. And in this case, instead of dealing with cumulative passing, we take the cumulative return. That's why it says R there. Okay. And obviously when we say returned, whatever is not returned will be passing. Whatever is not passing is returned. So it's either one of the two can be used. As I said, if I determined cumulative passing, I determine cumulative return. That's not a problem. It's straightforward. So instead of undersize here, as I shown in that arrow there in this table, what I'm looking for is the oversize or the returned cumulative return percent. Okay. So that's the R, and that's given by 100 by e the power of minus x by x prime power of b. So R, as I said, is mass retained, x is size in micron. Okay, from that previous table, the size in micron refers to my sieve aperture size, 500, 355, and so on. Okay, and B is the distribution parameter. Again, just like the previous example for the Gordon-Schumann plot, where I had the A for distribution parameter, we have a B for distribution parameter here. So it tells you whether you have a narrow size range or a very wide size range for the particles. And X is the size parameter. X is determined at value of R of 36.79%. Now I know that sounds very random. Why 36.79? So that will be a bit clearer in the next slide. Okay, so if I used the previous expression for R and take log scale and do again log scale, okay, we take that second equation on the slide, log of 100 by R equals b log of x minus b log of x prime plus log of e. Now, as I mentioned, I said the x prime is calculated at R value of 36.79 because if you took 36.79 for the value of R, log of 100 divided by 36.79 equals log of E. Okay, so if you had that, then you have a situation where x equals x prime. Okay, so always when we determine the size parameter, we go to a point on R scale at 36.79 and we determine the corresponding size on x-axis, and that will be your x prime. Okay, and that's why we have that 36.79, just in case you're wondering. Okay, so again, for the previous data, if you plotted log of 100 by R versus log of x, you get a straight line. Okay, and from that slope, you get the B, which is your distribution parameter, and you go to y-axis, point to 36.79, and then go to the linear fit. Okay, from the linear fit, you can determine. So you go to the linear fit, and then on the x-axis, you can determine the x prime, which is the size parameter. Okay, again, as I say, maybe in a given operation, this method is more common. Okay, if you can see those examples, so here it's not really straight line, but as you can see here, it is reasonably straight line. Maybe for some data or for some plants, this works really well, so they might just follow this method. So there's no, I can't say one is better than the other, okay, in terms of method or in terms of which one to use. For some operations, depending on the nature of the ore, depending on the mill and everything that goes with it, one may be applied well than the other. But again, what's more important is stick to one method, apply that consistently, and that will give you an idea of how to control the operation. Okay. Okay, thank you guys for listening. So I have some exercises to do. Hopefully you guys are not bored yet. And because those are exercises, hopefully you can participate a little bit more. But anyway, If you have questions on this one and the previous topic on sampling, please feel free to ask. Any question? I think Elias's computer is problematic at this stage. I think as soon as you turn it on, I get a big echo. I don't know if it's better to use someone else's computer, maybe. Maybe you can keep use mute, Elias, and use someone else's if anyone has a question.
ይሰማል?
ይሰማኛል ግን ኤኮ አልጠፋም። አንተ ኦን ስታደርገው ኤኮ አለ። አሁን አጠፋኸው። ስታጠፋው ኤኮ አይሰማኝም። ልክ ኦን ስታደርገው ተደጋግሞ ነው የሚመጣው ድምጽ።
አሁን ይሰማል አይደል?
እስቲ የሌላ ሰው ሌላ ክላስ ውስጥ ያለ ሌላ ሰው ካለ የእነሱን ኮምፒውተር ሞክሩ እስቲ። ያንተ እንደዛው እንደጠፋ ይቆይና የሌላ ሰው ካለ
እዚህ ላይ ይሰማል።
ሴም አይ ዶንት ኖ ዋትስ ጎይንግ ኦን። አንድ አይነት ነው። አንተም ኦን ስታደርገው ኤኮ አለው። ስለዚህ የሆነ ቦታ የሆነ ማይክ ኦን ሆኗል። አይ ዶንት ኖ የማን እንደሆነ ግን ማየት አልቻልኩም እዚህ ጋር። ኦኬ እስቲ አውራ። አሁን ራቅ አለ እንጂ ይሰማል ድምጽ። ኤልያስ የሚል ሁለት ነው የሚታየኝ። ለምን እንደሆነ አላውቅም። ሁለት ቦታ ነው የከፈትከው መሰለኝ ኤልያስ። ኦ ሁለት ዲቫይስ ለአንድ ሞባይል እና የሆነ ኮምፒውተር ላይ የተከፈተ ነገር አለ። እስቲ አሁን አውራ። አሁን ሌላኛውን ነው ያደረገው። አሁን ማውራት ትችላለህ። የሆነ ኤልያስ የሚል ኦን የሆነ ማይክ አለ። እስቲ ማውራት ከቻልክ አውራ አሁን። ኦኬ እያወራ ከሆነ አይሰማኝም። ስለዚህ የሚመስለኝ ኤልያስ ጋር ሁለት ዲቫይሶች አሉ። ኦን ስታደርገው ሁለቱም ኦን ይሆናሉ። ኢኮ የሚመጣው ለዛ ነው ማለት። ኦኬ እስቲ ብርሃኑ ያንተ ይሰማኛል?
ና በዚህ ጥያቄ
ኦኬ የብርሃኑ ይሰማኛል። ብርሃኑ አዱኛ የሚለው ይሰማኛል።
አሁን ይሰማል?
ኦኬ ይሰማል። አሁን ይሰማኛል።
እሺ የኔ ጥያቄ
ኦኬ
አሁን ይሰማል?
ይሰማኛል። ያሁኑ የኔ ጥያቄ ብሎ ነው ያቆመው እኔ ጋር። ስለዚህ የሚጠይቅ ሰው ካለ አይ ቲንክ እየተሰማኝ አይደለም ማለት ነው።
ፓርቲክል ሳይዝ ዲስትሪቢዩሽን ላይ ነው።
እሺ
የመጀመሪያው ቢከር ዲካንቴሽን ላይ as you said we already used to determine the particle size distribution based on the settling velocity. But particles may have the same settling velocity with different types. For example, if take a sample and samples having different size may have the same settling velocity, so they may settle at the same velocity. So how can we able to differentiate the sample size distribution having the same settling velocity?
So if samples are different sizes, they should have different settling velocity. So that's the main principle. Okay, so two particles with two different sizes, cannot have the same settling velocity. That is because if you look at Stokes' law here, if D varies, okay, the terminal velocity also varies. So when you say two particles with different sizes may have the same terminal velocity, that shouldn't be the case. I don't know if I understood your question. Okay, so for any given particle, there is one specific terminal velocity. If particles are larger than that size, they should have a different terminal velocity. If they're smaller than that size, they should have a different terminal velocity. So a specific terminal velocity should correspond to a specific particle size if all the other factors are constant. So if the density of the fluid and the density of particle doesn't change, okay, different sizes should have different terminal velocity. Does that make sense? All good, Elias? I can't hear. Okay, I'm sorry, but I can't hear anyone speaking. Or I don't know if anyone has a question.
Doctor, I just have one question.
Yeah.
We have seen different types of particle size analysis methods.
Yeah.
Which one is the better one? Which one is recommendable for most industries?
Yeah.
For example, there is different kinds of. We know that there is a processing plant for coal and for minerals.
Mm-hmm.
But which one is better to use?
Yeah, very good. So generally, if I have to pick a suitable method, it will be sieving, generally speaking. That's because it is cheaper and it's very practical because it addresses particle sizes that are very wide. Okay, so you can apply to finer particles, you can apply to coarse, and you can apply to intermediate particles. And those particles are usually what we deal with during processing plant operation anyway. But that doesn't mean it's a perfect method. So for example, if you come to coal can be a bit challenging because particles can be a little flat. And when particles are flat and not really close to spherical in shape, they don't actually pass through the sieves easily, and that can be challenging. It works, so I use sieving for coal particles, no problem, but it can have limitations. Okay, so you have to deal with a specific technique based on what you are doing in a typical operation. But if I have to just generally speak, then sieving would be a more practical way of doing it. If I wanted to be very accurate, if error is not allowed in my determination, then as I said, microscopy will be useful. But if I have access and if I want a very quick way of knowing particle size distribution, then I will use a laser sizer. But to keep an eye on my daily operation of a processing plant, sieving is probably the best to approach with. Does that make sense? I don't want to complicate things, but I'm just mentioning different things because it can be dependent on what you have in mind.
Yeah. Okay, thank you.
Yeah. Any other question?
Yes.
Yep.
My second question is on laser diffraction.
Yeah, yeah.
As you said, we use a beam of light just to analyze the particle size distribution on the case of laser distribution.
Yep.
As you said, the angle of diffraction, the scattering angle of diffraction tell us the particle size distribution.
Mm-hmm.
So how can the angle of diffraction, does it mean specific particles have a specific angle of distribution, diffraction? I mean.
Yes, so based on how coarse or how fine particles are, they will scatter the laser at different angles, okay, and at different intensities. So all the detectors do is somehow correspond angle of scattering to particle size. But I think the other thing I didn't mention there is we also need to quantify how particles move inside the equipment itself as well. Some particles move faster, some particles move slower, and we apply a theory of electrophoresis inside the equipment as well. But primarily, what it is trying to exploit in laser diffraction is the fact that bigger particles will reflect the laser at a wider angle, and therefore, if I get all wide angle scattering, it must be because I am measuring coarse particle sizes. But if the angle of scattering are different, then the corresponding particle size should be allocated to that as well. So that's why we say if narrow angles, then coarse particle. If wide angles are scattered, then smaller particles. But it's obviously a spectrum. I'm not talking about one end or the other end, but it is from wide scattering to narrow angle scattering. You have a spectrum, and therefore you have also a spectrum of particle sizes in that range as well. So I'm not just saying one extreme or the other. If it's wide, it is, of course, if it's wide scattering, then I can say smaller particle, but it is also a spectrum of scattering, not just one or two scatterings, okay, that we're referring to. So at the end of the day, from a laser sizer, I will get distribution of particles from 1 micron, 2 micron, 10 micron, 50 micron, 100 micron, all the ways to whatever particle size I have, okay? So I'm not getting fine or coarse only, I'm getting a complete spectrum based on that scattering angle, okay? That's what I'm trying to say. Okay, and any other question?
የለም ሌላ ጥያቄ የለም ጨርሰናል።
ሌላ ጥያቄ የለም? ኦኬ እሺ ጥሩ። አቤት
የመጀመሪያውን እናውራው መሰለኝ ስለ ላብ የተባለው
እሺ እሱን ከማውራታችን በፊት አንድ 10 ደቂቃ ብትሰጡን ኤግዛምፕል ልስጣችሁና ከዛ በኋላ ስለዛ ብናወራ ምን ይመስላል?
እሺ
ጥሩ እሺ ኦኬ ሶ ምንድነው ያሰብኩትኝ እዚህ ጋር አንድ ኤክሰርሳይዝ ፓርቲክል ሳይዝ ዲስትሪቢዩሽን በተመለከተ አይ ዶንት ኖ ከዚህ በፊት ሰርታችሁት ይሁን አይሁን ስለማላቅ ምናልባት ፋሚሊየር ልትሆኑ ትችላላችሁ ግን ኤኒዌይስ አንድ ኤግዛምፕል እንስራና ከዛ ወደ እንትን እንሄዳለን ሶ I think ይሄኛው ኤግዛምፕል ሳምፕሊንግ ላይ ነው። በጣም ከቅድሙ ጋር ኦልሞስት አንድ አይነት ጥያቄ ነው። ስለዚህ ብዙም ጊዜ ማባከን አያስፈልገው። ይሄን ሶሉሽኑን ሰጣችኋለሁ። ጀስት እዩትና ጥያቄ ካላችሁ አይ ቲንክ ማለት ዲስከስ ማድረግ እንችላለን። ስለ ፓርቲክል ሳይዝ ዲስትሪቢዩሽን ላይ ቅድም እንዳልኳችሁ so maybe we can have a data okay similar to the previous one where you take sieves of sizes of say 212, 150, 75, 53, 45 and 10 micron sieve sizes, and you did your sieving and you retained different masses in each of those sieves. Okay, so between say in the initial 212 micron sieve there was nothing retained, so 0. In the 150 micron sieve 70 gram was retained, 70.5. In the 75 micron sieve 189.9 gram was retained, and so on. Okay, so the questions there were to draw a sizing curve and determine P80 as I did earlier, and to plot different plots, so the Gordon-Schumann plot and the Rosen-Rammel plots. So to be able to do all those questions there, you need to determine the cumulative passing size and the retained sizes for each of those. So if I say, I guess for those who have computer or if you have calculator, you can just add all the masses in each of those sieves and you can get the total. So 70.5 plus 189.9 plus 25 plus 57 and so on. So get the total mass there, which is your initial sample mass. Then work out the percent. So again, 70.5 divided by the total mass should give you about 14.1%. Okay, 189.9 divided by the total mass should give you 38%. 25.5, sorry, 0.2 divided by the total should give you 5%, and so on. So that's how we work out the third column there. So when we say cumulative passing, maybe, I don't know, the easier way to do maybe to do the retained first, cumulative retained, and then come back and calculate cumulative passing, if that's easier for you. So initially, in the 212 micron, no mass was retained, which means the cumulative passing is 100%. Everything passes through that 212 micron sieve, that's why it is 0. Okay, so cumulative passing is 100% and cumulative retain will be 0, right? I hope that makes sense to everyone. The next sieve is 150 micron. Okay, so in that 150 micron, I have 70.5 grams retained, which corresponds to 14.1%. So the retained is in the first one, in 212, 0 is retained. In 150, 14.1 was retained, right? So the retained will be 14.1 for this case. What is the cumulative passing? The cumulative passing is simply 100 minus 14.1. Okay, so that's the second row. That's how you complete it. For the third one, at 75 micron, you have 38% corresponding to that particular sieve. If I wanted to know retained, I need to add the one prior to that plus this 75 micron to get the cumulative retained. Does that make sense? Because I already know 14% is retained initially in the 150 micron. Now I have retained 38 micron. So the cumulative retained will now be 14.1 plus 38%, right? So 14.1 plus 38 micron will be retained in that 75 micron size. So if I wanted cumulative, then I would say 100 minus the retained will give me the cumulative. Okay, makes sense? Again, go to this 53 micron. So it says 5% is retained in that one. Previously in the 75, I have 38. And prior to that, I have 14.1. So what is retained above the 53 will be 5 plus 38 plus 14.1 will give me the cumulative retained for the 53 micron. And you do the same for the other one. For the 45, retained is 11.6 plus 5 plus 38 plus 14. For 10 micron, I have 15.3 plus 11.6 plus 5 plus 38 plus 14.1 will give me cumulative retained. Once I have the cumulative retained, 100 minus the cumulative retained will give me cumulative passing. Okay, so I'm hoping it should look like this one. So the table should look like this one. So maybe I will just pause a couple of minutes for you guys to go through those numbers and tell me if you are all good with it. If someone doesn't understand what's going on here, maybe I can discuss a little bit more. Okay. ኦኬ እዛ ጋር ጥያቄ ያለው ሰው ካለ አሁን ብጠይቁኝ አሪፍ ነው። ምክንያቱም ማብራራት እችላለሁ የሆነ ክሊር ያልሆነ ነገር ካለ። ምክንያቱም ሜቢ ስትሬት ፎርወርድ ሊሆን ይችላል ለእናንተ አላቅም። ሜቢ ትንሽ ግራ የሚያጋባ ሊሆን ይችላል አላቅም። የማውቀው ስትጠይቁኝ ነው እና ሁሉም ሰው አንደርስታንድ የሚያደርግ ከሆነ መቀጠል እንችላለን። ጥያቄ ያለው ሰው አሁን መጠየቅ ይችላል። ኦኬ ነው። እንቀጥል ነው ጥያቄ አለ? ኦኬ ኦኬ ግልጽ ነው። ጉድ። ስለዚህ አንድ ይሄንን ካረግን በኋላ ኔክስት ማድረግ የምንችለው ምንድን ነው? ኤክስ አክሲስ ላይ ሳይዝ ነው የምናደርገው፣ ፓርቲክል ሳይዝ። ስለዚህ 212 150 75 ኤክስ አክሲስ ላይ ማድረግ እንችላለን። ዋይ አክሲስ ላይ ኮሙሌቲቭ ፓሲንግ ወይም ኮሙሌቲቭ ሪቴንድ የሚለውን እንጠቀማለን ማለት ነው። ዲፔንድስ ኦን ዊች ፕሎት ዌር ሉኪንግ ፎር። ፒኤቲ የሚባለውን ስንፈልግ ኤ ላይ እዛ ጋር ድሮ sizing curve and determine PAT የሚለው ጋር all we need to do is to plot cumulative passing on the y-axis and log scale of the particle size on the x-axis. Okay. If you did that, so አንደኛው የሰጠዋችሁ ፔፐር linear log scale ያለው እንደዚህ አይነት ነው። ስለዚህ cumulative passing 0 to 100 linear scale ነው። ሳይዝ ኤክስ አክሲስ ላይ ያለው ሎጋሪዝሚክ ስኬል ነው። ስለዚህ እነዛን ቁጥሮች ብታስገቡ ለምሳሌ 10 ማይክሮን ላይ ኮሙሌቲቭ ፓሲንጉ 16 ነው የሚለው። ኦኬ ስለዚህ 10 ማይክሮን ጋር 16 እዚህ አካባቢ ይሰጣችኋል የመጀመሪያው ዳታ። ኦኬ ቀጥሎ ያለው 45 ማይክሮን ነው። 45 ማይክሮን ላይ 31.3 ነው የሚለው። ስለዚህ 45 ቀጥሎ ያለው ዳታ ላይ ስትሄዱ 30.1 whatever እዛ አካባቢ ይሆናል። ስለዚህ እነዛ ዳታ ፖይንቶች ኤክስትራክት የተደረጉት ከቴብሉ ነው ማለት ነው። ኦኬ so once we do this, so there's no need for this to be straight line. It can be straight line but it may not be straight line. Okay, so you can try to fit something that may be describing your data, and once you do that you can go to the 80% passing. Okay, so y-axis 80% and go to the curve and then find the corresponding x value there, and that will give you the 80% passing size. So in this case, it gives you about 140 micron. So what it's saying is, in this graph here, in this table here, although it's not clear, at about 140 micron, 80% of the particles will pass through the sieve. So the 80% passing size will be about 140 micron. Okay. So hopefully you guys can practice and learn how to do this. So the next thing we can do is plot those standard plots I showed you. Again, we do exact same thing. We know this is what we want for a Gaussian-Schumann plot. What we need to plot is log of P, cumulative passing, versus log of X. So we have a log-log scale graph. Y is on log scale and X is on log scale. And we use those values from the graph. Okay, as I mentioned, at 10 micron, the Y is 16. At 45 micron, the Y is about 31. So we use those data points again. All that changed was the scale. The Y is now on log scale. Okay, the X is still on log scale. And once we do that, we can fit linear, draw a linear line through those data points, and we can determine the slope. Okay, or you can calculate the slope manually as well. Okay, so in this case, the slope is about 0.74. I told you this is what we call the distribution parameter. And to obtain the size parameter, you go to 100% passing. So on the y-axis, you go to 100 and go to the linear line and determine the corresponding x from the 100. Okay, and that's how you determine the sizing parameter. And for the Rosen-Ramler plot, all you need to do is log of 100 by r on the y-axis and determine the log scale of the size x on the x-axis. And if you did that, so አንዱ ሼር ያደረኳችሁ ፋይል የሮዝን-ራምለር ከርቭ ነው። Maybe I print አድርጋችሁ አይታችሁት ከሆነ looks a bit odd, the y-axis, but that is the scale we can use for this particular curve. Okay, and again we do exact same thing. So go to the table for corresponding x, we put the corresponding cumulative passing values. So sorry, in this case cumulative retained values, and then we plot a linear through it, and we can determine the slope and the size parameter from that. Okay, so hopefully it's not too bad, it's not too complicated, but if you have questions, go through it and let me know. Okay, ብዙ ጊዜያችሁን እንዳልወስድ ጥያቄ ካላችሁ you can ask now, አለበለዚያ ደግሞ ዲስከስን ማድረግ እንችላለን ቅድም ያልነውን ነገር። ግን ጥያቄ ካላችሁ ጠይቁ፣ doesn't matter, quick ጥያቄ መጠየቅ ትችላላችሁ።
On the graph part,
I'm sorry, it's not coming out right. አሁን ይሰማል። እሺ
on the graph, in the first graph, x-axis, on x.
This one or the previous one? This one?
The previous, yeah. And the x-axis, there's the size of particles at 10 micrometer.
The cumulative passing is 16. So we use not the minus 10, but the plus 10.
16.
I should have explained that.
As in plus 10.
Yeah, 16, yeah. So if you go to 10 on the log scale on the x-axis, that's the size.
Size? Is that 0?
Yeah. So the scale goes from 1, 10, 100, and 1000 on the x-axis.
Yeah.
Okay. So at 10, yeah.
Does it mean that at minus 10 micrometer the cumulative size is 0?
Yes, we're not taking that into consideration because here you can take this as a 0 for cumulative passing because there's nothing passing minus 10 micron. So we don't have a data for that actually.
Okay.
But you can take it as a 0. That's not a problem.
So on the graph part, can we extrapolate the the graph starting from
We-
0?
Yes, we can do that. Good question. So we can do that, but it depends
Yeah.
on what kind of fitting you have done into your graph. So in this case, you can try to put some polynomial fit and see if it follows your graph. If you have done that, then you can extrapolate that or interpolate that into 0. It's not a problem. Yeah, but it will have some error associated with it, but that can be done. Okay. Any other question?
ጥያቄ የለም አልኩ።
ጥያቄ የለም? እሺ ጉድ። ብዙ ስለማወራ አይ ዶንት ኖ ቦርድ እንዳትሆኑ አንዳንዴ እፈራለሁ። ፌስ ቱ ፌስ ቢሆን ሞር ኢንተራክሽን ይኖራል። አንዳንዴ የሆነ የሰዎችን ፊትም አይቼ አንዳንድ ነገሮችን መደጋገም እችላለሁ ኦር ምናምን፣ ግን ከዚህ ሆኖ በጣም አስቸጋሪ ነው ኢንጌጅ ማድረግ። ኤኒዌይ አይ ቲንክ አበረታታችኋለሁ። የሆነ በመሀል ጥያቄ ካላችሁ አስቆማችሁ መጠየቅ ትችላላችሁ። ፊል ፍሪ። ቅድም ወዳልነው ስንመለስ እንዳልኳችሁ 4 ፕራክቲካል ነው ያሰብኩት። አንደኛው ፕራክቲካል ሳምፕሊንግ ላይ ነው። ሁለተኛ ፕራክቲካል ሳይዚንግ ነው። ሆፕፉሊ አይ ቲንክ ሲቪንግ አትሊስት ማድረግ ትችላላችሁ ብዬ አስባለሁ። እዛ ላብ ውስጥ መኖር አለበት ሲቪንግ። ሌዘር ሳይዘር ይኑር አይኑር አላውቅም። ከሌላችሁ ሜቢ ዳታ ምናምን ከዚህ ሰፕላይ ማድረግ ይችላለሁ። እና አይ ቲንክ ሳይክሎሳይዘር እንኳን ያለ አይመስለኝም። ግን አትሊስት ባለው የሳይዚንግ ሜተድ ተጠቅመን አንድ ፕራክቲካል እዛ ላይ መስራት እንችላለን። ሶስተኛው ፕራክቲካል ክላሲፊኬሽን የሚባል ነው። ሃይድሮሳይክሎን ነው ብዙ ጊዜ የምንጠቀመው ለክላሲፊኬሽን። እሱን ቶፒክ ከቨር አላረኩትም፣ ግን አይ ዶንት ኖ ክላሲፋየር ያላችሁ አይመስለኝም። ግን አትሊስት ከሌለ ማድረግ የማይቻል ከሆነ ወይ ቪዲዮ ከዚህ ቀርጬ እንደዚህ ማሳየት ከቻልኩ ውልሲ ሃይድሮሳይክሎን ከዛ ዳታ ሰጥቻችሁ ሜቢ በዛ ላይ መስራት ትችላላችሁ። ግን አንድ ሞር ብትሰሩ በጣም ፈልገው ግራይንዲንግ ላይ ነው። ሆፕፉሊ ቦል ሚል አላችሁ። ቦል ሚል ካላችሁ ቦንድ ወርክ ኢንዴክስ እንዴት ዲተርሚን እንደሚደረግ አይ ቲንክ ጥሩ ፕራክቲካል እዛ ላይ መስራት እንችላለን። ይሄው ምንድነው ሃርድነስ ግራይንዳቢሊቲ ኦፍ ኦር እንዴት ዲተርሚን ይደረጋል የሚለውን ቦንድ ወርክ ኢንዴክስን ተጠቅመን ማድረግ እንችላለን። እሱም አይ ቲንክ እሱም ብታቁት ብትለምዱት ጥሩ ነገር ነው። ስለዚህ አራተኛው እሱ ነው። ራፍሊ about 3 ሰዓት፣ ሁሉም 3 ሰዓት አይፈጅም ኦፍ ኮርስ፣ ግን አይ ቲንክ ቦንድ ወርክ ኢንዴክስ ከ3 ሰዓት በላይ ሊፈጅ ይችላል ኦርጋናይዝድ ካልሆናችሁ። ግን እንደው ራፍሊ አቨሬጅ እንኳን ብንወስድ ለእያንዳንዱ 3 ሰዓት እንኳን ብንመድብ 4 ሴሽን ያስፈልገናል ማለት ነው። ለዚህ ደግሞ ሌክቸሩን ደግሞ ይሄንን እንደዚህ አይነት ሌክቸር ደግሞ ለመጨረስ ቢያንስ 4 ሴሽን እንደዚህ ቀጣይነት ያለው እንፈልጋለን። አሁን በሐሙስ የምናደርገው ከአሁን በኋላ 4 ያስፈልገናል ቢያንስ ካልቻላችሁ ማለት ነው። ከዛ ላይ ደግሞ ያው አሰስመንትም አላችሁ። ስለዚህ ማወቅ የፈለኩት አንደኛ ሴሚስተራችሁ ምን ያህል ነው የቀረው፣ ሁለተኛ ደግሞ እንዴት ነው የላቡን በተለይ እንዴት ነው ኦርጋናይዝ የምናደርገው የሚለው።
ሴሚስተሩ 1 ወር ነው የቀረው ነው ያሉት ዶክተር አቡበከር። ግን 1 ወር የተባለበት እኛ ዘግይተን የጀመርነው ከኖርማል ከሬጉላር ፕሮግራሙ 1 ወር ከምናምን 1 ወር ከ15 ቀን ምናምን ዘግይተን የጀመርነው እና የማጨርሱ ከሆነ ኤክስቴንድ እናደርጓለን የሚል አይነት እንትን ነው ትናንትና ነግሮን የነበረው።
እሺ፣
ስለዚህ እነሱን ያለውን ጊዜ እናማክራቸውና ኤክስቴንድ የሚደረግ ከሆነ በሬጉላር ፕሮግራሙ ማለቅ ይችላል። ጊዜም ተጨማሪ ጊዜም ማመቻቸት እንችላለን።
ኦኬ ጥሩ። ስለዚህ እንደዚህ እናርግ። አሁን ሌክቸሮቹ የሐሙሶቹን ዝም ብለን እናስኪዳቸው እስከ መጨረሻው ድረስ። ሜቢ አንድ ሌላ ተጨማሪ ካስፈለገን ኤክስቴንድ እንዲያደርጉ እንጠይቃለን። 5ኛ ካስፈለገን ግን በ4ቱ አኮሞዴት ለማድረግ ልሞክር ያለውን ነገር። ግን የፕራክቲካሉን እንዴት ነው የምታደርጉት?
የፕራክቲካሉን ጊዜ እናመቻችና እዚሁን ዶክተር አቡበከር የሚያሰሩ
ምንድነው ያልኳችሁ ገና ይሄንን ነገር አክሰፕት ከማድረጌ በፊት ሰው መድቡልኝ እዛ ብያቸዋለሁ ይሄንን የሚያግዝ እና ኦኬ ብለውኛል። አሁን በቅርብም ጠይቂያቸው ሰው ማዘጋጀት እንችላለን ብለዋል። እዛ እንደ አሲስታንት ነገር ላብ ውስጥ እንደ ቴክኒካል አሲስታንት ሰው ካለ ኦልሬዲ ማኑዋሉን ስለላኩትኝ ለእናንተም ሼር አድርጋችኋለሁ። ምን እንደሚሰራ ፕሮሲጀሩ ምኑ አለው እዛ ላይ ምን ማቴሪያል እንደሚያስፈልግ ምናምን አለው ምን ዳታ ኮሌክት ማድረግ እንዳለባችሁ ያሳያል። አሁን ያላወቁት የትኛውን ነው መስራት የምትችሉት የትኛውን ነው የማትችሉት የሚለውን ነው ከነሱ ነው እየጠበቅኩ ያለሁት። የጠየኳቸው እነዚህን አራቱን ነው የምንሰራው ግን ባላችሁ ፋሲሊቲ የትኛው ነው መስራት የሚቻለው የትኛው ነው የማይቻለው ብዬ ጠይቄያቸዋለሁ። መልሱን እየጠበቅኩ ነው። ግን ሐሳቡ ኤኒዌይ ሁሉም ይሰራል እንኳን ቢባል እዛ ቴክኒካል ስታፍ ያስፈልጋል የሚያግዝ አንደኛ። ሁለተኛ ምን ማድረግ እችላለሁ ኩዊክ የሆነ ቪዲዮ እንደዚህ አድርገን ይሄ ላብ የሚሰራው እንደዚህ ነው ይሄ ላብ የሚሰራው እንደዚህ ነው ብዬ ለእናንተ መንገር እችላለሁ አንደኛ። ለቴክኒካል ስታፎችም እዛ ፋሚሊየር ካልሆኑ እንደዚህ አድርጋችሁ አብራችሁ ስሩ ከልጆቹ ጋር ብዬ መንገር እችላለሁ።
እሺ ስለዚህ ነገ ዶክተር አቡበከር ክላስ ስላለን እነሱን እናማክራቸውና ለእናንተ ያው የሚሰራውን ይንገሯችሁ እኛ ከነሱ ጋር ታይም አሬንጅ ብናደርግ እስከ ዶክተር አቡበከር ጋር አማክረናቸው
ጥሩ ነው። ለዛ ቢሆን በጣም ጥሩ ነው። ሆፕፉሊ ያው እንዳልኩ አራት ብንሰራ ጥሩ ነው። ያው የሚቻለውን ብናደርግ ጥሩ ነው። ባይቻልም አይ ቲንክ ሀሳቤ ቢያንስ የሆነ ዳታ ዝም ብሎ አርቲፊሻል የሆነ ዳታ እንኳን ብሰጣችሁ የሆነ ኢንተርፕሪቴሽኑን ሪፖርት መጻፉን ምናምኑን በዛውም ስለምትለማመዱ አይ ቲንክ ኢትስ ወርዝ ዋይል እነዛም አትሊስት የማይቻሉትን ማለት ነው። ስለዚህ በዛ እንያዘው ጥሩ ነው።
እሺ ቪዲዮዎቹ አስቀድሞ ቢላኩልን እኛ ቶሎ ተዘጋጅተን እዛም እንዳናስቸግራቸው
ስለዚህ የላቦቹን ዝም ብዬ ሪኮርድ አድርጌ ልላክላችሁ ወይስ እንደዛ ይሻላል? እነዚህ ነው የሚሰሩት እነዚህ ላቦች ብዬ ኦኬ ጉድ ጥሩ በቃ እንደዛ ከሆነ እንደዛ አድርጌ ልክላችኋለሁ። እሱ ማኑዋሉንም ልክላችኋለሁ አብሬ።
እሺ እናመሰግናለን።
ኦኬ እሺ መልካም ኦኬ እሺ ጥያቄ ከሌላችሁ አይ ቲንክ በዚሁ መጨረስ እንችላለን ለዛሬ። ቴንክ ዩ በጣም ስለመጣችሁ እና አፕሪሺየት አደርጋለሁ። አንዳንድ ጥያቄዎቹ ምናምኑን ዲስከሽኑ አሪፍ ነው ቀጥሉበት።
እሺ እናመሰግናለን።
እሺ ኦኬ ቻው